Welcome to the Lumos. To understand the birth of the first stars, we must first understand the universe they were born into. Not the universe we see today, filled with galaxies and cosmic structures, but a younger, simpler cosmos, a universe just 380,000 years old. At this moment, something profound happened. The universe had expanded and cooled enough for a critical transition. Protons and electrons, which had been dancing freely in a seething plasma, finally slowed down enough to embrace. They formed neutral hydrogen atoms. This event is called recombination. A misleading name, really. There was no prior combination to recombine. It was simply the first time atoms could exist. Before this, the universe was opaque. Light couldn't travel freely. Photons were constantly scattered by free electrons, like trying to see through a dense fog. But when electrons bound to protons, the fog lifted. Light could finally travel unimpeded. The universe became transparent. This light is still with us today. It's the cosmic microwave background radiation, the faint afterglow of the Big Bang, a whisper of light from the universe's infancy. If you've ever seen static on an old television screen, about 1% of that static is this ancient light. Photons that have been traveling for 13.8 billion years finally reaching your eyes. But this transparency came at a cost. With no free electrons to scatter light, the universe went dark. Not just dark, profoundly dark. This was the beginning of the cosmic dark ages, a period that would last for hundreds of millions of years. Imagine this darkness, not the dark of a moonless night on Earth where stars still glitter, not the dark of a cave where your eyes eventually adjust. This was a darkness so complete that there were no stars to illuminate it, no galaxies, no light sources at all. Only the faint, fading glow of the cosmic microwave background, a universe filled with neutral hydrogen gas, helium traces, and the invisible pull of gravity. The universe at this time was remarkably smooth. Measurements of the cosmic microwave background show that density variations were tiny, about 1 part in 100,000, like a perfectly calm ocean with ripples no higher than a millimeter. But these tiny ripples were crucial. They were the seeds of everything that would come. Gravity, the universe's patient architect, began its work. Where matter was slightly denser, gravity pulled a little stronger. Where it was slightly less dense, matter flowed away. Over millions of years, these tiny fluctuations grow. Like snowflakes in an avalanche, they accumulated. The dark matter in the universe played a key role. Though we've never directly detected dark matter particles, we know they exist through their gravitational influence. Dark matter doesn't interact with light, only with gravity. It formed a cosmic web, invisible filaments connecting nodes of higher density. Ordinary matter, mostly hydrogen gas, flowed along these filaments, like water finding its way through a network of streams. This process was slow, so slow that human minds struggle to grasp it. Gravity is the weakest force in the universe, but it's relentless. Over tens of millions of years, it pulled hydrogen gas into increasingly dense regions. The universe was exhaling, preparing to inhale light. During this time, the universe continued to expand and cool. The temperature dropped from about 3000 Kelvin at recombination to less than 100 Kelvin. The gas became cold enough that hydrogen atoms could move slowly, resisting gravitational collapse. But gravity is patient. It kept pulling. The stage was set. The actors, hydrogen and helium. The script, gravity's slow pull. The setting, a universe waiting for its first spark. The Dark Ages were not empty. They were pregnant with possibility, a cosmic lullaby before the first cry of light. In this profound darkness, the universe was preparing for its greatest transformation, the birth of the first stars. But before we witness that birth, we must understand the cosmic nursery where these stars would form, the gathering of the first cosmic clouds.
The cosmic web, dark matter scaffolding. As the universe entered the Dark Ages, it wasn't a uniform expanse of gas. Hidden within the smoothness was a structure, a cosmic web woven by dark matter. To understand how the first stars formed, we must first understand this invisible architecture. Dark matter makes up about 27% of the universe. Ordinary matter, everything we can see, including stars, planets, and gas, makes up only 5%. The rest is dark energy, the mysterious force accelerating the universe's expansion. But dark matter is the key to structure formation. Unlike ordinary matter, dark matter doesn't interact with electromagnetic forces. It doesn't emit, absorb, or reflect light. It only interacts gravitationally. This makes it both elusive and essential. Because dark matter doesn't interact with light, it could begin collapsing under gravity much earlier than ordinary matter. While ordinary matter was still coupled to radiation in the early universe, dark matter was already feeling the pull of gravity. Computer simulations show how dark matter formed a cosmic web. Imagine a three-dimensional network of filaments, like the structure of a sponge. These filaments connect at nodes where dark matter density is highest. The voids between these filaments are vast, nearly empty regions of space. This dark matter web formed through a process called hierarchical structure formation. Small structures formed first, then merged to create larger ones. Tiny dark matter halos with masses perhaps 1,000,000 times that of our Sun were the first to collapse. These then merged to form larger halos, eventually reaching masses of 1,000,000,000 solar masses or more. Ordinary matter, primarily hydrogen gas with about 24% helium by mass, followed this dark matter scaffolding. Gas flowed along the dark matter filaments, like rivers feeding into lakes. At the nodes where filaments met, gas accumulated. This is where the first galaxies would eventually form. The process was remarkably efficient. Dark matter's gravitational pull created potential wells, regions where the gravitational potential was lower. Gas flowing into these wells gained kinetic energy, heating up as it fell deeper into the gravitational well. This heating would eventually allow the gas to collapse further and form stars. But there was a problem. As gas fell into these potential wells, it heated up. Hot gas exerts pressure, which resists gravitational collapse. For the gas to collapse further and form stars, it needed to cool down. Cooling mechanisms in the early universe were limited. Today, gas clouds cool efficiently through radiation from elements like carbon, oxygen, and iron. But in the early universe, these heavier elements hadn't been formed yet. The only elements were hydrogen and helium. Hydrogen can cool through atomic transitions, but only at temperatures above about 10,000 Kelvin. Below this temperature, hydrogen cooling becomes ineffective. Helium is even less effective at cooling. This meant that the first gas clouds couldn't cool below about 200–300 Kelvin. This cooling bottleneck had a profound effect on star formation. Because gas couldn't cool efficiently, it couldn't fragment into small clumps. Instead, only the largest gas clouds could collapse under gravity. This led to the formation of the first stars being extremely massive, hundreds of times more massive than our Sun. But we're getting ahead of ourselves. Before the first stars could form, the gas had to accumulate in sufficient quantities. This took time. Gravity is patient, but it's also persistent. Over tens of millions of years, gas continued to flow along dark matter filaments, feeding the growing halos. The first dark matter halos that could potentially form stars were relatively small by today's standards, about 1,000,000 times the mass of our Sun. But this was enough to pull in significant amounts of gas. As gas accumulated, the density at the center of these halos increased. Imagine standing inside one of these primordial gas clouds. What would you see? Not much visually. The cloud would be mostly transparent, with a faint glow from the cosmic microwave background radiation. This radiation, now redshifted to microwave wavelengths, would be absorbed and re-emitted by the hydrogen gas, creating a diffuse, uniform background. But if you could measure the density, you'd see variations. Tiny fluctuations in the distribution of gas, ripples in a pond. These were the birthplaces of the first stars. Gravity's fingers gently pressing, gathering matter into tighter knots. As the gas became denser, it began to spin, slowly at first, then faster. This is due to conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. As the gas cloud contracted, any slight initial rotation was amplified. The spinning gas began to flatten into a disk, like pizza dough stretched by a celestial chef. At the center of this disk, where the density was highest, the gas became hot and dense. This was the cradle of the first star. The process of gas accumulation wasn't smooth, it was turbulent. Gas flowing along filaments would collide at the nodes, creating shocks that heated the gas. Magnetic fields, though weak in the early universe, may have played a role in channeling gas flows. All these processes, gravity pulling, gas flowing, turbulence stirring, magnetic fields guiding, were happening simultaneously. Over millions of years, they sculpted the gas into structures that would eventually become the first stars. The universe was preparing its first hearth. The kindling was gathered. The spark was coming. But before we witness that spark, we need to understand what happens when gas becomes so dense and hot that it ignites nuclear fusion, the birth of a star.
The collapse, from gas cloud to protostar. At the center of a primordial gas cloud, something extraordinary was happening. Gravity, having gathered gas over millions of years, was now squeezing it with increasing force. The density at the cloud's core was rising dramatically. Temperature was climbing, pressure was building. This was the beginning of the end for the gas cloud, and the beginning of something entirely new. The collapse of a gas cloud to form a star is a battle between two forces: gravity pulling inward and pressure pushing outward. When gravity wins, the cloud collapses. When pressure wins, the collapse halts. For the first stars, gravity would ultimately win, but not without a struggle. As the gas cloud contracted, gravitational potential energy was converted into kinetic energy, the energy of motion. This kinetic energy then became thermal energy through collisions between gas particles. The cloud heated up. Initially, this heating wasn't a problem. The cloud could radiate away the excess energy. But as the cloud became denser, it became opaque. Radiation couldn't escape easily. The temperature at the center began to rise more rapidly. When the central temperature reached about 100 Kelvin, something important happened. The hydrogen molecules that had formed in the cold gas began to dissociate, break apart into individual hydrogen atoms. This process required energy, which came from the thermal energy of the gas. In effect, the gas was using its own heat to break apart molecules. This allowed the cloud to continue collapsing without heating up as much. This dissociation process continued until the temperature reached about 2000 Kelvin. By this point, most of the hydrogen molecules had broken apart. Now, the cloud was primarily atomic hydrogen, and it could no longer use molecular dissociation to cool. The collapse continued. The density at the center kept increasing. The temperature kept rising. When the temperature reached about 10,000 Kelvin, hydrogen atoms began to ionize, lose their electrons. This ionization process, like molecular dissociation before it, required energy. The gas used its thermal energy to ionize hydrogen, allowing further collapse. This phase of collapse is particularly interesting. The cloud was becoming a protostar, a hot, dense core surrounded by a collapsing envelope of gas.
The protostar wasn't yet a true star because nuclear fusion hadn't begun in its core, but it was getting close. The collapse wasn't perfectly spherical. Real gas clouds have rotation, turbulence, and magnetic fields. These factors cause the collapsing cloud to flatten into a disk, with the protostar forming at the center. This disk is called an accretion disk, a structure we now see around many young stars. Gas from the disk spiraled inward, feeding the growing protostar. As gas fell onto the protostar, it released gravitational potential energy, heating the protostar further. The protostar's surface temperature at this stage was perhaps 5,000 to 10,000 Kelvin, similar to our Sun's surface temperature today. But the protostar was much larger, perhaps 100 times the radius of our Sun. The protostar continued to accrete mass from the surrounding disk. This accretion process wasn't smooth. It was variable, with bursts of accretion followed by quieter periods. These variations may have caused fluctuations in the protostar's brightness. As the protostar grew more massive, its core became hotter and denser. The pressure at the center increased dramatically. When the core temperature reached about 10 million Kelvin, something remarkable happened. Nuclear fusion began. This wasn't a sudden explosion, it was a quiet ignition. Protons, hydrogen nuclei, were moving so fast that when they collided, they could overcome their mutual electrostatic repulsion. They fused together, forming helium nuclei. In the process, a small amount of mass was converted into a large amount of energy, according to Einstein's famous equation, E equals mc squared. This energy release was crucial. It created an outward pressure that resisted further gravitational collapse. For the first time, the protostar had an internal energy source. It was no longer just a hot ball of gas collapsing under gravity. It was a star. The first star was born. Let's call it Lumos Primus, a name for the first light bringer. Lumos Primus was unlike any star we see today, made only of hydrogen and helium, no heavier elements, no carbon, no oxygen, no metals. Astronomers call these population 3 stars. They were cosmic pioneers. Their size was staggering. Computer simulations suggest that the first stars were typically between 100 and 300 times the mass of our Sun. Why so massive? Remember the cooling bottleneck we discussed earlier. Without heavier elements, gas clouds couldn't cool efficiently. Cooling allows gas to fragment into smaller clumps. Without it, only the largest clumps could collapse. So the first stars were giants. These massive stars were also extremely hot. Their surface temperatures reached 100,000 Kelvin or more, 10 times hotter than our Sun. This high temperature meant they emitted most of their energy in the ultraviolet part of the spectrum. Ultraviolet radiation is much more energetic than visible light. The birth of Lumos Primus was not an event. It was a process. Gravity squeezed, gas heated, fusion ignited, light escaped, all unfolding over millennia, a quiet revolution in the heart of a cosmic cloud. But this was just the beginning. The light from Lumos Primus would go on to transform the universe itself. It would ionize the surrounding hydrogen gas. It would begin forging the first heavy elements. And it would pave the way for the next generation of stars. The universe's first sunrise was about to dawn.
The first light. Properties of primordial stars. Lumos Primus, the first star, was now shining in the cosmic darkness. But what was this star really like? To understand its impact on the universe, we need to explore its properties in detail. The first stars were fundamentally different from the stars we see today. The most striking difference was their mass. As we've discussed, population 3 stars were typically 100 to 300 times more massive than our Sun. For comparison, the most massive stars known today are about 150 times the Sun's mass. The first stars were true giants. This enormous mass had several consequences.
First, these stars had incredibly high core temperatures. While our Sun's core temperature is about 15 million Kelvin, the core of a 300 solar mass population 3 star would reach about 100 million Kelvin. At these temperatures, nuclear fusion reactions occurred at a furious pace. Second, these stars were extremely luminous. Luminosity, the total energy output per second, depends strongly on mass. For massive stars, luminosity scales roughly as mass to the power of 3.5. This means a star 100 times more massive than our Sun would be about 1,000,000 times more luminous. A star 300 times more massive would be about 30 million times more luminous. These stars were so bright that despite their distance, they would have been visible to the naked eye if you could somehow travel back in time to observe them. Of course, no eyes existed back then to see them. The universe was still hundreds of millions of years away from the first life. Third, population 3 stars had very short lifetimes. Despite their enormous mass, they burned through their fuel at a prodigious rate. A star like our Sun has a total lifetime of about 10 billion years. A 100 solar mass population 3 star would live for only about 3 million years. A 300 solar star would live for less than 1,000,000 years. In cosmic terms, these lifetimes are mere blinks. The first stars were born, lived, and died in the time it takes for galaxies to form. Their lives were short, but their impact was profound. The surface temperatures of population 3 stars were also extreme. While our Sun has a surface temperature of about 5,800 Kelvin, population 3 stars had surface temperatures of 100,000 Kelvin or more. This high temperature was due to their low metallicity, the lack of elements heavier than hydrogen and helium. In modern stars, elements like carbon, nitrogen, and oxygen in the outer layers absorb some of the radiation coming from the core, effectively cooling the stellar surface. But population 3 stars had no such elements. Their outer layers were transparent to radiation, allowing more energy to escape from deeper layers. This resulted in higher surface temperatures. These high surface temperatures meant that population 3 stars emitted most of their energy in the extreme ultraviolet part of the spectrum. Ultraviolet radiation with wavelengths shorter than 91.2 nanometers, called Lyman continuum radiation, is particularly important because it can ionize hydrogen atoms. When a hydrogen atom absorbs a photon with this much energy, the electron is stripped away. The atom becomes ionized. This process is crucial for understanding how the first stars transformed the universe. The spectra of population 3 stars would have looked very different from modern stars. Spectra are like stellar fingerprints. They show which wavelengths of light are absorbed or emitted by chemical elements. Population 3 stars would have shown only hydrogen and helium lines, with no traces of heavier elements. Another important property of population 3 stars is their stellar winds. All stars lose mass through stellar winds, streams of charged particles flowing away from the star. For massive stars, these winds can be quite strong. But population 3 stars might have had weaker stellar winds than modern stars of similar mass. Why? Because stellar winds are driven by radiation pressure on atoms in the stellar atmosphere. In modern stars, elements like iron and other metals absorb radiation effectively, transferring momentum to the gas and driving strong winds. But population 3 stars had no metals. Their atmospheres were transparent to radiation, so radiation pressure was less effective at driving winds. This meant that population 3 stars retained more of their mass throughout their lives. When they died, they would have left behind more massive remnants, either black holes or neutron stars. The structure of population 3 stars was also different. Without heavy elements, their interiors were simpler. Energy transport occurred primarily through radiation rather than convection. Convection, the movement of hot gas upward and cool gas downward, is important in modern stars for mixing material and transporting energy. But in population 3 stars, convection was limited to the outer layers. These stars were also more compact than modern stars of similar mass. Without metals to provide additional opacity, their radiative zones were more transparent, allowing energy to flow more easily. This resulted in smaller radii for a given mass. The evolution of population 3 stars followed a different path than modern stars. As they burned hydrogen in their cores, they contracted and heated up. But without metals, their evolution was more rapid. They spent less time on the main sequence, the stable phase of hydrogen burning, than modern stars. When they exhausted the hydrogen in their cores, population 3 stars faced a crisis. Without nuclear fusion to provide outward pressure, gravity began to win the battle again. The core contracted, heating up even further. For the most massive population 3 stars, this led to a series of fusion reactions, each producing heavier elements. Hydrogen fused to helium, helium fused to carbon, carbon fused to oxygen, and so on, up the periodic table. But this process couldn't continue indefinitely. For the most massive stars, the end came quickly and violently. The first stars were cosmic pioneers, different in almost every way from the stars we see today. But their most important characteristic was their ultraviolet radiation. This radiation would go on to transform the universe itself, ending the cosmic dark ages and initiating the epoch of reionization. But before we explore that transformation, we need to understand what happens when these massive stars reach the end of their lives. The death of the first stars was as dramatic as their birth.
Stellar death, supernovae, and black holes. The lives of the first stars were short, but their deaths were spectacular. When a massive star exhausts its nuclear fuel, gravity wins the final battle. The core collapses and the star explodes in a supernova. But for the first stars, these explosions were unlike anything we see today. Let's follow the final moments of Lumos Primus, our hypothetical 300 solar mass population 3 star. After living for less than 1 million years, it had fused most of its core hydrogen into helium. As the hydrogen fuel ran out, the core began to contract under its own weight. This contraction released gravitational potential energy, heating the core further. When the core temperature reached about 100 million Kelvin, helium fusion began. In this process, 3 helium nuclei fused to form a carbon nucleus. This is called the triple alpha process, named because helium nuclei are also known as alpha particles. Helium fusion releases even more energy than hydrogen fusion. For a brief time, the star stabilized again. But this stability was short-lived. Helium burns faster than hydrogen, and within a few 100,000 years, the helium in the core was exhausted. Now, the core contracted again. Temperatures rose to about 600 million Kelvin, and carbon fusion began. Carbon nuclei fused to form magnesium, sodium, and neon. This process released more energy, temporarily halting the collapse. But for the most massive stars, this cycle of fusion and collapse continued. Each successive fusion process released less energy than the previous one and burned faster. Carbon fusion lasted only a few thousand years. Then oxygen fusion began, lasting only a few hundred years. Silicon fusion followed, lasting mere days. At each stage, the star was building heavier elements in its core, like an onion with layers of different elements. The outermost layer was still hydrogen, then helium, then carbon, oxygen, and so on, with the heaviest elements at the center. But this process couldn't continue indefinitely. When the core began to fuse silicon into iron, something fundamental changed. Iron is special. It has the most tightly bound nucleus of all elements. Fusing iron into heavier elements doesn't release energy, it absorbs energy. For Lumos Primus, this was the beginning of the end. With no more energy coming from fusion, the core could no longer support itself against gravitational collapse. The core, now made primarily of iron, began to collapse at nearly a quarter the speed of light.
In less than a second, the core, originally about the size of the Earth, collapsed to a radius of only about 20 kilometers. The density became so high that protons and electrons were crushed together to form neutrons and neutrinos. This process is called photodisintegration and electron capture. The collapse released an enormous amount of energy, equivalent to the total energy output of our Sun over its entire lifetime, released in just a few seconds. Most of this energy was carried away by neutrinos, nearly massless particles that interact very weakly with matter. But some of this energy drove a shock wave outward through the star. This shock wave, traveling at about 10,000 kilometers per second, blew the star apart in a supernova explosion. For Lumos Primus, this explosion was unlike any supernova we observe today. Because of its enormous mass, the explosion was incredibly energetic. The total energy released was perhaps 100 times that of a typical modern supernova. These explosions are sometimes called pair instability supernovae or pulsational pair instability supernovae. Pair instability supernovae occur in very massive stars when the core temperature becomes so high that gamma rays spontaneously produce electron-positron pairs. This process converts radiation energy into mass, reducing the radiation pressure that supports the star against gravity. The result is a runaway collapse and explosion. In a pair instability supernova, the entire star is destroyed. No compact remnant like a neutron star or black hole is left behind. Instead, all the material is ejected into space, including the heavy elements forged in the star's core. But not all population 3 stars died this way. Stars at the lower end of the mass range, perhaps 40 to 100 solar masses, might have died differently. These stars could have left behind neutron stars or black holes. The most massive black holes formed from population 3 stars could have had masses of 50 to 100 solar masses. These black holes would have been the seeds for the supermassive black holes we now see at the centers of galaxies. Over billions of years, they could have grown by accreting gas and merging with other black holes. The supernova explosions of population 3 stars had profound effects on the universe. First, they ejected the heavy elements forged in the star's core. These elements, carbon, oxygen, nitrogen, iron, and more, were now scattered into the surrounding gas. This enrichment of the interstellar medium was crucial for the formation of the next generation of stars. Stars that form from gas containing heavy elements, called population 2 stars, are different from population 3 stars. They can be smaller, live longer, and have different structures. Second, the explosions released enormous amounts of energy into the surrounding gas. This energy heated the gas, making it harder for new stars to form immediately. This feedback mechanism regulated star formation in the early universe. Third, the explosions produced powerful shock waves that compressed nearby gas clouds. This compression could trigger the collapse of these clouds, leading to new bursts of star formation. The death of one star could trigger the birth of many others. Fourth, the explosions accelerated charged particles to nearly the speed of light. These cosmic rays would have traveled through the early universe, ionizing gas and contributing to reionization. Finally, the explosions produced gravitational waves, ripples in the fabric of space-time itself. These waves would have traveled outward at the speed of light, carrying information about the explosion. Though too weak to detect with current technology, future gravitational wave detectors might be able to observe similar events from the early universe. The death of Lumos Primus marked the end of an era. The first generation of stars was gone, but their legacy lived on. The elements they forged would become part of new stars, new planets, and eventually new life. The energy they released would transform the universe from neutral to ionized. The first stars were born in darkness, lived briefly, and died spectacularly. But in their short lives, they changed the universe forever. They ended the cosmic dark ages and began the epoch of reionization. They turned the universe from a simple place of hydrogen and helium into a complex cosmos filled with heavy elements and diverse structures. The death of the first stars was not an end. It was a beginning. The beginning of the universe we see today.
The cosmic dawn, reionization. When the first stars ignited, their light did more than simply illuminate the cosmic darkness. It transformed the very nature of the universe. This transformation, the transition from a neutral, opaque universe to an ionized, transparent one, is called reionization. It was one of the most important events in cosmic history. To understand reionization, we need to go back to the cosmic dark ages. After recombination, when electrons combined with protons to form neutral hydrogen atoms, the universe became transparent to radiation. But this transparency was limited. Photons from the cosmic microwave background could travel freely, but there were no other light sources. The universe was filled with neutral hydrogen gas. Hydrogen is the simplest atom, one proton, one electron. In its neutral state, hydrogen can absorb photons with specific energies, particularly those in the ultraviolet part of the spectrum. When the first stars formed, they began emitting intense ultraviolet radiation. This radiation had enough energy to ionize hydrogen, to strip electrons from protons. When a hydrogen atom absorbs a photon with energy greater than 13.6 electron volts, the ionization energy of hydrogen, the electron is ejected. This process doesn't just create free electrons and protons, it also changes how the universe interacts with radiation. Ionized gas is transparent to most radiation, while neutral gas is opaque. By ionizing the hydrogen, the first stars made the universe transparent again. Reionization didn't happen all at once. It was a gradual process that occurred over hundreds of millions of years. The first stars formed in small, isolated regions. Their ultraviolet radiation created bubbles of ionized gas around them. Within these bubbles, light could travel freely. Between them, the universe was still neutral. Over time, these bubbles grew. New stars formed within the ionized bubbles, where gas was already enriched with heavy elements from previous supernovae. These new stars produced more ultraviolet radiation, expanding the bubbles further. The bubbles eventually merged. When two ionized bubbles overlapped, the neutral gas between them was quickly ionized. This process continued until the entire intergalactic medium was ionized. The timeline of reionization is still being studied, but current evidence suggests it began when the universe was about 200 to 300 million years old and was largely complete by the time the universe was about 1 billion years old. How do we study reionization? One way is by looking at distant quasars. Quasars are extremely bright objects powered by supermassive black holes. Some quasars are so far away that their light was emitted when the universe was less than 1 billion years old. As light from these quasars travels through the universe, it passes through intergalactic gas. If this gas is neutral hydrogen, it absorbs specific wavelengths of light, creating dark lines in the quasar spectrum. These lines are called Gunn-Peterson absorption. By studying the spectra of distant quasars, astronomers can determine how much neutral hydrogen existed at different times in the universe's history. The absence of Gunn-Peterson absorption in quasars from when the universe was about 1 billion years old suggests that reionization was largely complete by that time. Another way to study reionization is through the cosmic microwave background itself. The radiation from the cosmic microwave background can scatter off free electrons in the ionized gas. This scattering creates a characteristic polarization pattern that can be measured. Observations from the Planck satellite and other instruments have provided evidence for reionization. The data suggests that reionization began around redshift 15, when the universe was about 250 million years old, and was largely complete by redshift 6, when the universe was about 1 billion years old. But what was driving reionization? The first stars were certainly important, but they may not have been the only contributors. Other potential sources of ionizing radiation include the first black holes. As we discussed, the first stars may have left behind black holes when they died. These black holes could have accreted gas, forming the first quasars. Quasars emit enormous amounts of ultraviolet and X-ray radiation, which could contribute to reionization. Gamma ray bursts.
These are extremely energetic explosions thought to be associated with the deaths of massive stars. They produce intense bursts of gamma rays that could ionize hydrogen over large distances. Decaying dark matter particles. Some theories suggest that dark matter particles might decay and produce ionizing radiation. However, there's no direct evidence for this process. Current evidence suggests that the first stars were the primary drivers of reionization, with quasars becoming more important toward the end of the process. Reionization had profound effects on the universe. First, it heated the intergalactic gas. The energy from ionizing radiation raised the temperature of the gas from about 10 Kelvin to perhaps 10,000 Kelvin or more. This heating affected how gas flowed into galaxies and how stars formed. Second, reionization suppressed the formation of small galaxies. Before reionization, gas could cool efficiently and collapse into small dark matter halos. But after reionization, the ultraviolet background radiation heated the gas, making it harder for small halos to retain gas. This created a minimum mass for galaxy formation. Third, reionization changed the way galaxies evolved. The heated gas took longer to cool and collapse into galaxies, slowing down star formation. This feedback mechanism helped regulate the growth of galaxies in the early universe. Finally, reionization made the universe transparent to ultraviolet radiation. This allows astronomers today to observe distant galaxies and quasars. Without reionization, the universe would still be opaque to much of the radiation we use to study it. The process of reionization was complex and inhomogeneous. Some regions reionized earlier than others. The distribution of galaxies and dark matter played a crucial role. Regions with higher density reionized first because they formed stars earlier and in greater numbers. Computer simulations help us understand this process. The most sophisticated simulations model not only the formation of stars and galaxies, but also the propagation of ionizing radiation through the universe. These simulations show that reionization was a patchy process, with ionized bubbles growing and merging over time. One of the most exciting recent developments in this field is the discovery of galaxies from the epoch of reionization. The James Webb Space Telescope, launched in 2021, has detected galaxies that existed when the universe was only a few 100 million years old. These galaxies provide direct evidence for the early stages of reionization. The study of reionization is closely tied to the search for the first stars. While we haven't directly observed the first stars yet, we're getting closer. Future telescopes and observatories, like the planned Extremely Large Telescope and the Square Kilometre Array, will provide even more detailed views of the early universe. Reionization marks the end of the cosmic dark ages and the beginning of the universe we see today. It was the universe's first sunrise, a gradual dawn that transformed the cosmos from darkness to light. But reionization was only part of the story. The first stars and their deaths also enriched the universe with heavy elements, setting the stage for the formation of planets and eventually life. The cosmic dawn was not just about light, it was about the creation of the building blocks of complexity. As we continue our journey, we'll explore how these heavy elements were distributed throughout the universe, and how they led to the formation of the first galaxies. The universe was no longer a simple place of hydrogen and helium. It was becoming a complex, diverse cosmos filled with the seeds of future wonders.
The first galaxies, assembly of cosmic structures. The formation of galaxies is intimately connected to the dark matter halos we discussed earlier. These halos provided the gravitational wells where gas could accumulate and cool. The first galaxies formed in the most massive dark matter halos at the time. When did the first galaxies form? Current evidence suggests that the first galaxies began forming when the universe was about 200 to 300 million years old. This is roughly the same time when the first stars were forming, but galaxies are larger structures that take longer to assemble. The process of galaxy formation is complex and hierarchical. Small structures form first, then merge to create larger ones. This is called bottom-up structure formation. The first galaxies were relatively small by today's standards, perhaps 1,000,000 times the mass of our Sun, compared to the Milky Way's trillion solar masses.
How do we study these early galaxies? One way is through deep imaging with telescopes like Hubble and James Webb. These telescopes can detect galaxies that are so far away that their light has been traveling for over 13 billion years. When we look at these galaxies, we see them as they were when the universe was young. Another way is through spectroscopy. By analyzing the light from distant galaxies, astronomers can determine their composition, temperature, and motion. This information helps us understand how galaxies formed and evolved. The James Webb Space Telescope has revolutionized this field. Since its launch, it has detected numerous galaxies from the epoch of reionization. Some of these galaxies existed when the universe was only 300 to 400 million years old. These galaxies are surprisingly bright and massive, suggesting that galaxy formation in the early universe was more efficient than previously thought. What were these first galaxies like? They were probably very different from modern galaxies like the Milky Way. For one thing, they were much smaller. The first galaxies may have had masses of only 1 million to 1 billion solar masses compared to the Milky Way's trillion solar masses. They were also irregular in shape. Modern galaxies like the Milky Way have well-defined shapes, spiral arms, central bulges, and so on. But the first galaxies were likely chaotic with no clear structure. They were still in the process of assembling. The first galaxies were also forming stars at a furious rate. Some of the galaxies detected by Webb are forming stars hundreds or even thousands of times faster than the Milky Way today. This intense star formation was fueled by the abundant gas in the early universe. The stars in these first galaxies were a mix of population 3 and population 2 stars. The very first stars to form were pure population 3 stars, made only of hydrogen and helium. But as these stars died and enriched the surrounding gas with heavy elements, subsequent generations of stars contained small amounts of heavier elements. These are called population 2 stars. Population 2 stars are still relatively metal poor compared to stars like our Sun, which are called population 1 stars. The study of stellar populations helps astronomers understand the history of star formation in galaxies. The first galaxies were also much denser than modern galaxies. The universe was smaller then, so galaxies were closer together. This proximity led to frequent interactions and mergers between galaxies. Galaxy mergers were important in the early universe. When two galaxies merge, their gas clouds collide, triggering bursts of star formation. The merged galaxy can also grow by accreting gas from the surrounding intergalactic medium. Over time, these processes built up larger and larger galaxies. The Milky Way itself formed through the merger of many smaller galaxies over billions of years. In fact, astronomers have identified streams of stars in the Milky Way that are remnants of past mergers. The first galaxies also contained the first supermassive black holes. These black holes, with masses millions of times that of our Sun, are found at the centers of most large galaxies today. How did they form so quickly in the early universe? One possibility is that they formed from the direct collapse of massive gas clouds. In the early universe, before reionization, gas could cool efficiently and collapse directly into a black hole without fragmenting into stars first. These direct collapse black holes could have had masses of 10,000 to 1 million solar masses. Another possibility is that they grew from the remnants of the first massive stars. As we discussed, the first stars could have left behind black holes with masses of 50 to 100 solar masses. These black holes could have grown rapidly by accreting gas and merging with other black holes. The growth of supermassive black holes is closely tied to galaxy evolution. As black holes accrete gas, they release enormous amounts of energy. This energy can heat the surrounding gas, preventing it from cooling and forming stars first. This feedback mechanism regulates the growth of both the black hole and its host galaxy. The first galaxies also played a crucial role in reionization. While individual stars contributed to ionizing the intergalactic medium, galaxies as a whole were the primary drivers. The combined ultraviolet radiation from all the stars in a galaxy could create large ionized bubbles around it. As galaxies grew and merged, these ionized bubbles expanded and eventually overlapped, completing the reionization process. The study of galaxy formation and reionization are thus closely connected. The first galaxies also enriched the intergalactic medium with heavy elements. When massive stars in these galaxies died as supernovae, they ejected heavy elements into the surrounding gas. Some of this gas escaped from the galaxies and mixed with the intergalactic medium. This enrichment had important consequences. Heavy elements allow gas to cool more efficiently, which promotes star formation. They also make the gas less transparent to ultraviolet radiation, which affects how radiation propagates through the universe. The distribution of heavy elements in the early universe is still an active area of research. Astronomers study this by looking at absorption lines in the spectra of distant quasars. These absorption lines reveal the composition of gas clouds along the line of sight. One of the most exciting discoveries in recent years is the existence of galaxies at extremely high redshifts. The James Webb Space Telescope has detected galaxies that existed when the universe was only 300 to 400 million years old. These galaxies are challenging our understanding of galaxy formation. Some of these galaxies are surprisingly massive and bright. How could they have formed so quickly? One possibility is that they formed earlier than we thought, perhaps when the universe was only 100 to 200 million years old. Another possibility is that they formed more efficiently than our models predict. The study of the first galaxies is also closely tied to the search for the first stars. While we haven't directly observed the first stars yet, we're getting closer. Future telescopes and observatories will provide even more detailed views of the early universe. The formation of the first galaxies marks an important transition in cosmic history. It was during this period that the universe began to look like it does today, filled with galaxies, stars, and black holes. The cosmic dark ages were truly over, and the universe was entering its adolescence. But the story doesn't end here. The first galaxies were just the beginning. Over billions of years, they would evolve into the diverse population of galaxies we see today: spirals, ellipticals, irregulars, and more. Each type of galaxy has its own story to tell, shaped by its unique history of formation and evolution. As we continue our journey, we'll explore how galaxies evolve over time and how they interact with their environment. We'll also look at the formation of the first galaxy clusters, the largest structures in the universe. The universe was becoming increasingly complex, with structures forming on all scales. The first galaxies were the universe's first cities, places where matter came together in dense concentrations, where energy was produced in vast quantities, and where the building blocks of complexity were forged. They were the first steps on the long road from a simple, uniform universe to the cosmos we see today.
The cosmic web, large-scale structure. As we zoom out from individual galaxies, we begin to see the largest structures in the universe. Galaxies are not randomly distributed in space. Instead, they form a cosmic web, a vast network of filaments and nodes that spans the observable universe. This cosmic web is one of the most striking features of our universe, and it holds clues to the universe's formation and evolution. The cosmic web is not a physical structure like a spider web. It's a distribution of matter, mostly dark matter, that forms a network of filaments connecting dense regions called nodes. The filaments themselves are made of dark matter and gas, while the nodes are where galaxy clusters form. Between the filaments are vast voids, regions of space with very few galaxies. These voids can be enormous, stretching tens or even hundreds of millions of light years across. In contrast, the filaments and nodes are where matter is concentrated. How did this structure form? The answer lies in the tiny density fluctuations we discussed earlier. After inflation, the universe was very nearly uniform, but with tiny variations in density. Overdense regions had slightly more matter than underdense regions. Gravity amplified these variations over time. Matter in overdense regions attracted more matter, making them even denser.
Matter in underdense regions float away, making them emptier. This process is called gravitational instability. Dark matter played a crucial role in this process. Because dark matter doesn't interact with radiation, it could begin collapsing earlier than ordinary matter. Dark matter formed the scaffolding for the cosmic web, with ordinary matter following later. The cosmic web we see today is the result of billions of years of gravitational evolution. Small structures formed first, then merged to create larger ones. This hierarchical structure formation is a key prediction of the current cosmological model. How do we study the cosmic web? One way is through galaxy surveys. By mapping the positions of millions of galaxies, astronomers can trace the underlying structure of the cosmic web. The Sloan Digital Sky Survey, for example, has mapped over 1 million galaxies, revealing a web-like structure on large scales. Another way is through computer simulations. Cosmological simulations model the evolution of the universe from the Big Bang to the present day. These simulations can follow the formation of the cosmic web in detail, showing how dark matter halos merge and how galaxies form within them. The largest cosmological simulations, like the Millennium Simulation and the Illustris Simulation, follow billions of particles in a computational box billions of light-years across. These simulations have been remarkably successful in reproducing the observed structure of the universe. The cosmic web has several characteristic features. First, it's highly clustered. Galaxies are not randomly distributed. They tend to cluster together. This clustering is quantified by a statistical measure called the two-point correlation function. Second, the cosmic web has a filamentary structure. Long, thin filaments connect nodes of high density. These filaments can be hundreds of millions of light-years long. Third, there are large voids between the filaments. These voids are not completely empty. They contain some galaxies, but they are much less dense than the filaments and nodes. Fourth, the cosmic web has a hierarchical structure. Small structures merge to form larger ones. Galaxy groups merge to form galaxy clusters, which in turn merge to form superclusters. The largest structures in the universe are superclusters. These are collections of galaxy clusters and groups that are gravitationally bound together. Our own Milky Way is part of the local group, which is part of the Virgo supercluster. Superclusters themselves are not gravitationally bound. Instead, they are part of larger structures called filaments or walls. The cosmic web is often described as having a sponge-like structure, with dense walls surrounding large voids. One of the most striking features of the cosmic web is its scale. The largest structures we see today are hundreds of millions of light-years across. Yet, when we look at the cosmic microwave background, we see that the universe was very smooth at early times. How did such large structures form? The answer lies in the nature of dark energy. Dark energy is the mysterious force that is causing the expansion of the universe to accelerate. Before dark energy became dominant, gravity could pull matter together over large scales. But now, dark energy is pushing matter apart, limiting the growth of structure. The transition from matter-dominated to dark energy-dominated expansion occurred when the universe was about 9 billion years old. Before this time, the universe was decelerating due to gravity. After this time, it began accelerating due to dark energy. This transition has had a profound effect on the cosmic web. In the matter-dominated era, structures could grow continuously. But in the dark energy-dominated era, the expansion of the universe began to accelerate, making it harder for gravity to pull matter together. As a result, the largest structures we see today are probably the largest that will ever form. The cosmic web also has important implications for galaxy formation. Galaxies form at the intersections of dark matter filaments, where gas can accumulate and cool. The properties of a galaxy, its mass, shape, and star formation rate, are influenced by its location in the cosmic web. Galaxies in dense clusters, for example, tend to be elliptical and have little ongoing star formation. Galaxies in less dense environments, like our Milky Way, tend to be spiral and have more ongoing star formation. This is called galaxy morphology density relation. The cosmic web also affects the distribution of heavy elements. When galaxies form stars, they produce heavy elements that are ejected into the surrounding gas. Some of this gas falls back into the galaxy, but some escapes into the intergalactic medium. The intergalactic medium is not uniform. It's denser near galaxies and filaments and less dense in voids. Heavy elements are transported through the intergalactic medium by galactic winds and other processes, enriching different regions of the cosmic web. The study of the cosmic web is closely tied to the study of dark energy. Dark energy affects the expansion history of the universe, which in turn affects how structures grow. By measuring the distribution of galaxies on large scales, astronomers can constrain the properties of dark energy. One of the most exciting future projects in this field is the Euclid mission, a space telescope designed to map the cosmic web in unprecedented detail. Euclid will measure the positions and shapes of billions of galaxies, allowing astronomers to study the cosmic web and dark energy with high precision. Another important project is the Dark Energy Spectroscopic Instrument, DESI, which is measuring the spectra of tens of millions of galaxies and quasars. These spectra provide information about the distances to these objects, allowing astronomers to map the three-dimensional structure of the cosmic web. The cosmic web is not just a distribution of galaxies. It's a dynamic structure that evolves over time. Galaxies move along filaments, falling toward nodes where galaxy clusters form. Gas flows along filaments, feeding the growth of galaxies and clusters. The cosmic web also affects the propagation of light through the universe. Light from distant galaxies is bent by the gravity of matter in the cosmic web, a phenomenon called gravitational lensing. By studying this lensing, astronomers can map the distribution of dark matter in the cosmic web. The cosmic web is a testament to the power of gravity and the nature of dark matter. It shows how simple initial conditions, tiny density fluctuations, can evolve into the complex structure we see today. It also shows how the universe has changed over time, from a smooth, simple place to a complex, diverse cosmos. As we continue our journey, we'll explore how the cosmic web has evolved over time and how it will continue to evolve in the future. We'll also look at the fate of the universe, how dark energy will shape its ultimate destiny. But first, let's take a closer look at the building blocks of the cosmic web, the galaxy clusters that form at its nodes. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies, as well as large amounts of hot gas and dark matter. The study of galaxy clusters provides important insights into the formation and evolution of the cosmic web. The cosmic web is the largest structure in the universe, but it's made of smaller structures that are equally fascinating. From galaxies to galaxy clusters to superclusters, each scale has its own story to tell. Together, they form a tapestry of cosmic evolution that spans billions of years and billions of light years. The cosmic web is not just a scientific concept. It's a reminder of our place in the universe. We live on a planet that orbits a star, that is part of a galaxy, that is part of a group, that is part of a cluster, that is part of a supercluster, that is part of the cosmic web. We are connected to the largest structures in the universe through a chain of cosmic evolution that stretches back to the Big Bang. The cosmic web is also a reminder of the power of gravity. Over billions of years, gravity has transformed a smooth, simple universe into a complex, diverse cosmos. It has pulled matter together into galaxies, clusters, and superclusters, creating the structure we see today. As we continue to study the cosmic web, we're not just learning about the universe's past, we're also learning about its future.
Heavy elements, forging the building blocks of life. The universe began with the simplest elements, hydrogen and helium. But the universe we see today is filled with a rich diversity of elements: carbon, oxygen, nitrogen, iron, and more. These heavier elements are the building blocks of planets, life, and everything we see around us. How did these elements form? The answer lies in the life cycles of stars.
The process of creating heavier elements from lighter ones is called nucleosynthesis. There are several types of nucleosynthesis, each occurring in different environments and producing different elements. The first type of nucleosynthesis occurred in the first few minutes after the Big Bang. This is called Big Bang nucleosynthesis. During this period, the universe was hot and dense enough for nuclear reactions to occur. Protons and neutrons combined to form deuterium, an isotope of hydrogen, then helium, and trace amounts of lithium. Big Bang nucleosynthesis produced a universe that was about 75% hydrogen and 25% helium by mass, with tiny amounts of lithium and other light elements. This composition matches the observations of the oldest stars and the cosmic microwave background, providing strong evidence for the Big Bang model. But Big Bang nucleosynthesis couldn't produce heavier elements. The universe expanded and cooled too quickly. To create heavier elements, we need the extreme conditions found in stars. The second type of nucleosynthesis occurs in the cores of stars during their lifetimes. This is called stellar nucleosynthesis. In stars like our Sun, hydrogen fuses to form helium in a process called the proton-proton chain. In more massive stars, hydrogen fuses to form helium through the CNO cycle, which involves carbon, nitrogen, and oxygen as catalysts. When stars exhaust the hydrogen in their cores, they begin fusing helium into carbon. This happens through the triple alpha process, where 3 helium nuclei fuse to form a carbon nucleus. This process requires temperatures of about 100 million Kelvin, which occur in the cores of stars that have exhausted their hydrogen fuel. For stars more massive than about 8 times the mass of our Sun, the fusion process continues. Carbon fuses to form neon, sodium, and magnesium. Neon fuses to form oxygen and magnesium. Oxygen fuses to form silicon and sulfur. Silicon fuses to form iron. Each successive fusion process releases less energy than the previous one and requires higher temperatures. The process stops at iron because fusing iron into heavier elements doesn't release energy, it absorbs energy. Iron has the most tightly bound nucleus of all elements. The third type of nucleosynthesis occurs when massive stars die in supernova explosions. This is called supernova nucleosynthesis. During a supernova, the extreme conditions, temperatures of billions of Kelvin and densities greater than that of atomic nuclei, allow for the rapid capture of neutrons by atomic nuclei. This process, called the R process, or rapid neutron capture, produces many of the heaviest elements in the periodic table, including gold, platinum, and uranium. The R process is so fast that it can create very neutron-rich isotopes that then decay to form stable elements. Supernova nucleosynthesis also produces lighter elements through other processes. For example, the explosion can fuse lighter elements together, and the intense radiation can break apart nuclei, creating a variety of isotopes. The fourth type of nucleosynthesis occurs in the outer layers of stars like our Sun. This is called asymptotic giant branch nucleosynthesis. In these stars, convection brings material from the core to the outer layers, where it can be transformed by nuclear reactions. AGB nucleosynthesis is particularly important for producing carbon and nitrogen. It also produces isotopes like lithium, beryllium, and boron through a process called spallation, where cosmic rays break apart heavier nuclei. The fifth type of nucleosynthesis occurs when 2 neutron stars merge. This is called kilonova nucleosynthesis. In 2017, astronomers observed the merger of 2 neutron stars for the first time. The event produced gravitational waves, gamma rays, and optical light. Analysis of the light showed that the merger produced heavy elements like gold, platinum, and uranium through the R process. Kilonova nucleosynthesis is now recognized as an important source of heavy elements in the universe. It may be the primary source of elements like gold and platinum. The distribution of heavy elements in the universe tells a story of cosmic evolution. The oldest stars in our galaxy, which formed when the universe was young, have very low amounts of heavy elements. These are called metal-poor stars. In astronomy, all elements heavier than helium are called metals. Younger stars, like our Sun, have higher amounts of heavy elements. This is because they formed from gas that had been enriched by previous generations of stars. The Sun, for example, has about 2% of its mass in elements heavier than helium. The study of metal-poor stars provides important insights into the early universe. These stars preserve the chemical composition of the gas from which they formed, allowing astronomers to study the products of the first supernovae. One of the most exciting discoveries in recent years is the existence of stars with extremely low amounts of heavy elements. These stars, sometimes called hyper-metal-poor stars, have less than 1/10,000th the amount of iron found in the Sun. They may have formed from gas that was enriched by only one or a few supernovae. The analysis of these stars can tell us about the properties of the first supernovae. For example, the relative amounts of different elements can indicate the mass of the supernova progenitor and the type of explosion. Heavy elements are not just interesting from a scientific perspective, they are essential for life as we know it. Carbon, nitrogen, and oxygen are the building blocks of organic molecules. Phosphorus is a key component of DNA and ATP. Iron is essential for hemoglobin, which carries oxygen in our blood. The fact that these elements are present on Earth is a consequence of cosmic evolution. The carbon in your cells, the oxygen you breathe, the iron in your blood, all were forged in stars that lived and died billions of years ago. As the astronomer Carl Sagan famously said, "We are made of star stuff." The journey of heavy elements from stars to planets is a complex one. When stars die, they eject heavy elements into the interstellar medium. This gas then cools and collapses to form new stars and planets. Some of the heavy elements condense to form dust grains, which are the building blocks of planets. In our own solar system, the planets formed from a disk of gas and dust surrounding the young Sun. The inner planets, like Earth, are made primarily of rock and metal, while the outer planets are made primarily of hydrogen and helium. This distribution reflects the temperature gradient in the early solar system. The study of meteorites provides important insights into the formation of our solar system. Some meteorites, called chondrites, are primitive objects that have changed little since the solar system formed. They contain small grains called calcium aluminum-rich inclusions, or CAIs, which are the oldest known solids in the solar system. The analysis of these grains shows that they formed from material that was enriched by multiple generations of stars. The isotopic composition of the grains provides a fingerprint of the nucleosynthetic processes that produce them. Heavy elements also play a crucial role in the evolution of galaxies. As we discussed earlier, heavy elements allow gas to cool more efficiently, promoting star formation. They also affect the appearance of galaxies, the colors of stars, the properties of nebulae, and so on. The distribution of heavy elements in galaxies is not uniform. The centers of galaxies tend to have higher amounts of heavy elements than the outer regions. This is because star formation is more efficient in the centers and because supernovae are more common in regions with higher stellar density. The study of heavy elements in galaxies is called galactic archaeology. By measuring the amounts of different elements in stars at different locations in a galaxy, astronomers can reconstruct the history of star formation and chemical evolution in that galaxy. One of the most important tools in this field is spectroscopy. By analyzing the light from stars or galaxies, astronomers can determine which elements are present and in what amounts. Each element has a unique spectral fingerprint, allowing precise measurements of chemical composition. The James Webb Telescope has opened a new window on the study of heavy elements in the early universe. By observing distant galaxies, Webb can detect the spectral signatures of heavy elements when the universe was only a few 100 million years old.
These observations are providing important insights into the early stages of chemical evolution. The story of heavy elements is also a story of cosmic recycling. Elements are created in stars, ejected into space, and then incorporated into new stars and planets. This recycling has been going on for billions of years, creating the rich diversity of elements we see today. The ultimate fate of heavy
We've journeyed through the birth of the first stars, the formation of galaxies, and the creation of heavy elements. Now, we arrive at perhaps the most remarkable consequence of cosmic evolution, the emergence of life. How did the universe transform from a simple, uniform state to a place where complex structures like planets, life, and consciousness could exist? The story of life begins with heavy elements. As we've discussed, elements like carbon, oxygen, nitrogen, and phosphorus are essential for life as we know it. These elements were forged in stars and distributed throughout the universe by supernovae and other stellar processes. But how did they come together to form the complex molecules necessary for life? The first step in this process is the formation of interstellar molecules. In the cold, dense clouds of gas and dust between stars, simple molecules like hydrogen, H2, carbon monoxide, CO, and water, H2O, can form. These molecules form on the surfaces of dust grains, where atoms can stick together and react. Over time, more complex molecules can form. Astronomers have detected over 200 different molecules in interstellar space, including organic molecules like methanol, CH3OH, formaldehyde, H2CO, and even amino acids like glycine. These discoveries show that the building blocks of life are common in the universe. One of the most important environments for the formation of complex molecules is protoplanetary disks, the disks of gas and dust that surround young stars. These disks are where planets form, and they are also where complex chemistry can occur. In protoplanetary disks, the temperature decreases with distance from the central star. Close to the star, only refractory materials like rock and metal can condense. Farther out, volatile materials like water ice can condense. This temperature gradient affects the composition of planets that form at different distances. The study of protoplanetary disks has been revolutionized by telescopes like the Atacama Large Millimeter Submillimeter Array. ALMA has observed disks in unprecedented detail, revealing rings, gaps, and spiral structures that are likely caused by forming planets. As planets form in these disks, they can acquire the complex molecules that were created in the disk. Some of these molecules may have been delivered to the surfaces of planets by comets and asteroids, which are remnants from the early solar system. The next step in the emergence of life is the formation of self-replicating molecules. On Earth, this step occurred about 4 billion years ago, when the planet was only about 500 million years old. The exact process is still unknown, but scientists have proposed several hypotheses. One hypothesis is that life began in a primordial soup of organic molecules in the early oceans. Energy from lightning, UV radiation, or hydrothermal vents could have driven the formation of more complex molecules, eventually leading to the first self-replicating systems. Another hypothesis is that life began at hydrothermal vents on the ocean floor. These vents release hot, mineral-rich water into the cold ocean, creating a chemical gradient that could have driven the formation of complex molecules. The minerals at the vents could have provided a surface for molecules to assemble and react. A third hypothesis is that life began in clay minerals. Clay minerals have layered structures that can concentrate organic molecules and catalyze chemical reactions. Some experiments have shown that clay minerals can promote the formation of RNA-like molecules. Regardless of where life began, the key step was the emergence of a molecule that could store information and replicate itself. On Earth, this molecule was likely RNA, ribonucleic acid. RNA can both store genetic information and catalyze chemical reactions, making it a candidate for the first self-replicating molecule. The transition from chemistry to biology is one of the most profound transitions in the history of the universe. Once self-replicating molecules appeared, evolution by natural selection could begin. Molecules that replicated faster or more accurately would become more common, leading to the evolution of more complex systems. Over time, these simple systems evolved into the first cells. Cells are the basic units of life. They have a membrane that separates them from their environment, they can metabolize energy, and they can reproduce. The emergence of cells was a crucial step in the evolution of life. The first cells were probably simple prokaryotic cells, similar to modern bacteria. These cells lacked a nucleus and other complex organelles. They were the dominant form of life on Earth for about 2 billion years. About 2 billion years ago, a revolutionary event occurred. A prokaryotic cell engulfed another prokaryotic cell, but instead of digesting it, the two cells formed a symbiotic relationship. This event, called endosymbiosis, led to the evolution of eukaryotic cells, cells with a nucleus and other organelles. Eukaryotic cells are more complex than prokaryotic cells. They have a nucleus that stores DNA, mitochondria that produce energy, and other organelles that perform specialized functions. The evolution of eukaryotic cells was a major step toward the evolution of complex multicellular life. The next major step was the evolution of multicellular organisms. Multicellularity allows for cell specialization. Different cells can perform different functions, making the organism as a whole more efficient. Multicellularity evolved independently in several different lineages, including animals, plants, and fungi. The evolution of complex life on Earth was not a smooth process. It was punctuated by several mass extinction events, where a large fraction of species went extinct in a relatively short period of time. The most famous of these is the extinction that killed the dinosaurs 66 million years ago, but there have been several others. Mass extinctions are important in the history of life because they create ecological opportunities. After a mass extinction, the surviving species can diversify to fill the niches left vacant by the extinct species. This can lead to the evolution of new forms of life. The evolution of intelligence is perhaps the most remarkable outcome of biological evolution on Earth. Humans are not the only intelligent species on Earth. Many other animals, including dolphins, elephants, and crows, show impressive cognitive abilities. But humans are unique in the extent to which we have developed technology and culture. The emergence of intelligence has had a profound effect on the planet. Humans have transformed the Earth's surface, altered its climate, and even begun to venture into space. We are the first species on Earth to understand the universe and our place in it. But the story of life is not just about Earth. The universe is vast, and the conditions that led to life on Earth may exist elsewhere. The search for life beyond Earth is one of the most exciting frontiers in science today. One of the most important questions in astrobiology is whether life is common or rare in the universe. On one hand, the building blocks of life are common in the universe. On the other hand, the steps from chemistry to biology may be very difficult. The search for life beyond Earth focuses on three main areas: Mars, the outer solar system, and exoplanets. Mars is a promising target because it once had liquid water on its surface, and it may still have liquid water underground. Several missions to Mars are currently searching for signs of past or present life. The outer solar system is also promising. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both have subsurface oceans of liquid water. These oceans are in contact with rocky seafloors, which could provide the chemical energy needed for life. Exoplanets, planets orbiting other stars, are perhaps the most promising targets in the search for life. The Kepler Space Telescope has discovered thousands of exoplanets, and some of them are in the habitable zone of their stars, the region where liquid water could exist on the surface. The James Webb Space Telescope is now studying the atmospheres of some of these exoplanets, looking for signs of life. For example, the presence of oxygen and methane together in an atmosphere could be a sign of biological activity, because these gases react with each other and would not both be present unless they were being continuously replenished. The discovery of life beyond Earth would have profound implications for our understanding of our place in the universe. It would show that the transition from chemistry to biology is not unique to Earth and that life may be common in the universe. But even if life is common, intelligent life may be rare. The evolution of intelligence on Earth required a series of unlikely events, including the extinction of the dinosaurs, which allowed mammals to diversify. It's possible that similar events are rare on other planets. The search for intelligent life beyond Earth is the focus of the SETI, Search for Extraterrestrial Intelligence project. SETI uses radio telescopes to search for signals from other civilizations. So far, no definitive signals have been found, but the search continues. The story of life on Earth is a story of cosmic evolution. It begins with the Big Bang, continues with the formation of the first stars and galaxies, the creation of heavy elements, and the formation of planets.